among the two welding techniques of the gas welding, uh, there is one which is called forward welding, and another is the backward welding. And the primary difference is in terms of the inclination or orientation of the welding torch with respect to the welding direction. So say if this is the side view of the seats which are being joined, the plates which are being joined, and or this is the welding direction, and the torch is oriented in the direction of welding. Okay, so there is an angle, say 35 or 45 degree. So in this case, this is the direction when the torch is pointing towards the direction of the welding. So this is the section which has been welded, and this is the section which is yet to be welded. Okay, so when the flame comes out of the torch, it preheats the metal which is yet to be welded. So the one thing which is realized is the preheating of the base metal. There are many metals which are very crack sensitive because of high cooling rates. So when preheating is done, the cooling rate is reduced. So the cracking tendency of those metals is reduced when this kind of preheating is facilitated through the forward welding. Okay, so there are like the medium or high carbon steels, medium and high carbon steels, and many hardenable steels, many cast irons. All these are very crack sensitive when subjected to the welding. So when so during the forward welding of such hardenable steels, the preheating is realized of the base metal during the welding itself automatically without use of external source of heat for preheating purpose. So that in turn reduces the cracking tendency. So first it reduces the cooling rate, and reduction in cooling rate reduces the hardening and embrittlement tendency. So reduces the embrittlement tendency, and this in turn leads to the reduced cracking of the weld joint. So if the weld joint is made with the cracks, then certainly it doesn't perform good. So this is one of the main benefit apart from the high welding speed, because preheated metal melts faster. So high speed welding is realized. So these are the two main benefits you can say of the forward welding. Reduced cracking tendency and increased welding speed, and this is primarily important in case of the hardenable metals like medium high carbon steel or hardenable steels or cast irons, etc. Okay, this is all about the forward welding. Okay, the another one is the backward welding. In backward welding, actually, the inclination or orientation of the welding torch is opposite to that of the welding direction. Say this is the welding direction, then torch is pointing direction opposite to that of the welding direction. Okay, so the flame is, say this is the welded section, so the flame is directed towards the already welded section, is directed towards this already welded section. So that means heat is continued to be supplied to the welded portion already. So this heat helps to facilitate the post-weld heat treatment. Welding is performed, but still if you are supplying the heat in case of the backward welding technique, then the post-weld heat treatment is realized. So this post-weld heat treatment reduces the residual stresses. These are developed primarily due to the differential heating and cooling, because in welding what we do, we do very localized heating along a particular zone only. So the zone next to the weld joint is heated and cooled rapidly, while the metal away from the weld area remains at under the ambient conditions. So differential heating and cooling develops the residual stresses. When post-weld heat treatment is performed, these residual stress magnitude is reduced. So this is one good thing because it reduces the mechanical performance, it reduces the distortion tendency, means the plates will go out of the shape. They will earlier, if they were flat, then it may bend in any of the directions. So the residual stress is reduced. And another good thing which happens after the post weld heat treatment is the improvement in maybe mechanical properties. So this is another thing which is realized. So the residual stress reduction and the improvement in mechanical properties, these are the two good things which are realized when the backward welding is performed. So these are the two unique features associated with these two welding techniques. Now coming to the arc welding, that's another joining process. Basically, this is also a type of the fusion welding process, where in fusion welding process, where the components to be joined are brought to the molten state through the application of the heat, and then whatever molten weld pool is formed, that on solidification will be leading to the metallurgical continuity. So this is how the weld is developed in all fusion welding processes. The difference is primarily in terms of the heat source. Earlier we have used the gas oxygen gas fuel mixture for producing flame. So flame of the high temperature is used to bring the edges of the plates to the molten state in the gas welding. In case of arc welding, it is the arc which is used to generate the heat. So basically in arc heat generation, what happens, we have one power source and we have another the base metal which is to be joined. So the power source is usually connected to the negative terminal of the power source so the electrode is connected to the negative terminal of the power source, okay, and the positive terminal of the power source is connected to the base metal. When we use this kind of the connectivity to have the arc, okay, so in this case the arc, say the current I is current setting is say I, and the potential difference applied across the electrode and the base metal is V. So V into I, when there is an arc, the current I flows through the arc and generates the heat. So I into V is used to define as the power of the arc. It gives us the heat generated in terms of the joule. Okay. So it is say 10 volt multiplied by 400 ampere. So it is 4000 joules. So in simplified form, it is written as 4 kilojoule. Since the heat source is moving at a certain speed like this, okay. So say the speed is 100 mm per minute, right? This is the very common speed, 100 mm per minute, okay. So means it is 0.1 meter per minute, right? 0.1 meter per minute, okay. So now what we do, since it is in terms of this is the heat being generated per second, it is in watt actually. So what we have to do is this 100 is to be divided by 60 to get the speed in mm per second, okay. So he say if we take instead of 100, if we take 2, right, so 120, so it will be 120, and then in that case we'll be getting 2 mm per second, okay. So let's say the heat generated Vi and the amount of heat being delivered per unit time, that is per second, by the arc in a particular zone. So let us divide it by S. So when VI, that is 4 kilojoule, okay, 4 kilojoule, when it is divided by 2 mm per second, okay, so what we get basically 2 kilojoule, second and second will be cancelled, so here 2 kilojoule per mm. This is how the net heat input is obtained. So the simple formula for having the net heat input is net heat input being applied during the welding is VI by S. Okay. So here the voltage, the current applied, and the welding speed. So this heat input in arc welding typically ranges from 0.5 to say 5 kilojoule per mm. Okay. So this is one thing. Your voice is not clear. Actually, I'm not able to hear it clearly. Are you saying something? Anyway, so depending upon the kind of connectivity that we are having, we can say we can have the different types of the polarity. So polarity in arc welding. This is the another aspect. Okay. So when we have a power source having a DC power source, say positive terminal and negative terminal. So when say the positive terminal, okay, this is negative terminal, this is positive terminal. Say you have one electrode and one workpiece which is to be joined. So when the negative terminal is connected to the electrode and the positive terminal is connected to the base metal, it forms one typical kind of polarity that is called DC SP, state polarity, or DC electrode negative. So in case of the DC electrode negative, the lesser heat, about 33% of the arc heat is generated in the electrode side, and 66% of the heat is generated in the workpiece side. But when we use the reverse polarity, so because of this greater heat generation, we get the deeper penetration in case of the DC SP or electrode negative polarity. Say when we use the power source, DC power source, having the positive polarity connected to the electrode and negative polarity is connected to the workpiece. In that case, say negative terminal connected to the workpiece and electrode is connected to the positive terminal, like this. To two-thirds of the heat, that is about 66% of the heat is generated in the electrode side, and about 33% of the heat is generated in the workpiece side. So because of this, weld cross section is small, penetration is less. Okay. So if we compare the penetration for DC EN and DC EP, then what we will notice that the weld size is large, penetration is deep. Okay. On the DC EP electrode positive, lesser heat generation, electrode weld size is reduced and penetration is also reduced. All right. But when we use AC, where polarity will keeps on swinging between the EN and EP, because the polarity changes in every half cycle, so we get the penetration and the weld size in between of the DC EN and DC EP. Okay. I think I have talked about all these things. I can recall. So that's about the polarity. And for the AC, we simply use the transformers, and for the DC, it is the rectifiers and the generators which are used. Okay. And it uses the electrodes. So the different types of the electrodes are basically used. These electrodes are like the coated electrode and the bare electrode. These are also called uncoated electrode. Okay, so the coated electrodes can be coated with the fluxes, or these can be coated with the copper. So for submerged arc welding and for your MIG welding, the copper coated the electrodes are used, while the simple flux coated electrodes are used in the shielded metal arc welding. Okay, shielded metal arc welding. So there are different functions which are performed by these the the coatings which are used in the shielded metal arc welding. So the copper helps to improve the electrical current carrying capacity, as well as it reduces the corrosion. So corrosion resistance is basically enhanced, and the electrical current carrying capacity of the electrode is enhanced by the use of copper coating. So as far as the flux is concerned, flux has the certain elements which helps to improve the arc stability. So arc ignition of the arc and its stability or its maintenance. Both are improved due to the presence of low ionization potential elements like sodium and potassium are sodium and potassium are added in the electrode coating. Apart from this, it has a few hydrocarbons, wood dust, charcoal. So all these things produce the CO and CO2, which helps. These are basically inactive gases and provides the protection to the weld. Apart from this, there also can be some elements, additional alloying elements for modifying the composition of the weld metal, modification of weld composition. Okay, so alloying also can be realized through this. Then there is one more. These coatings are basically electrical insulators. So arcing and short circuiting due to the contact with the other the components or the metallic pieces during the welding, that is avoided. So insulating insulation role is also performed by these coatings. The fluxes also help to form the thick slag. Basically, the slag, viscous slag is formed. So when the viscous slag is formed, it uh, protects the weld from the atmospheric gases. So oxide and nitride formation is reduced. At the same time, the viscous slag reduces the fluidity of the molten metal, and because of this reduction in fluidity of the molten metal, you can easily apply the molten weld metal in the vertical, horizontal, and overhead positions. So overhead, vertical, and horizontal welding is facilitated through the formation of the viscous slag. Fluxes are designed in such a way that the slag is also being formed. Slag is lighter than the molten metal itself. So when the slag is formed, it floats over the surface. Say this is the molten weld metal. So slag being lighter, it starts floating over the surface of the weld metal. So that's how it protects from the atmospheric gases. It reduces the cooling rate of the weld metal as well. So both of these good things are performed by the slag. So as far as the stick electrode or SMAW electrodes are concerned, these are found in the different diameters like 3.2, 4, 5, 6, 8, sorry, 8, 9, etc. And in found in the length of say 350 to 450, right? Now, if you see, I think I can recall, probably I have talked about all these things, but anyway, I'm just covering, therefore I'm covering it a little fast. So now coming to the uh, electrode selection. Huh? Electrode selection. So the selection of the electrode means which will include the metal of the electrode, the diameter of the electrode. Okay. Uh, and this will also include the consideration of the flux or the current to be used. We can use both DC as well as AC. DC welding is easier because arc is stable, easy to strike the arc as compared to the AC welding. Okay, so the first thing which is kept in mind for selection of the electrode for developing the SMAW weld joint is that mostly we go for, like, if the two same types of the metals are being joined AA, then we'll try to use the electrode which is of the matching composition. So the electrode of the matching composition and the properties is chosen. This is the first thing. But when we come across the situation where A is being welded with the B, that is the different metal, then we may use the third type of the electrode. So dissimilar or different type of the electrode can also be chosen so that it is compatible to both A and B. So here C type of electrode may be chosen, which is acting as a bridge between the A and B. So property requirement in terms of the tensile strength, so matching properties, or the composition. These are the two important things. We try to go for electrode which can offer us the desired mechanical properties in terms of the toughness, strength, and percentage elongation. Okay, and it is of the matching composition. Another important thing in selection of the electrode is about the size of the electrode that we want to go for. There is a common electrode size like 3.2, 4, or 5. So if the thickness of the base is more, then certainly it needs more heat for through thickness penetration, and more heat can be generated by using the high welding of current. Say, if earlier you were using for thin sections 200, then you may need 400 ampere current for having through thickness penetration in while welding the thick sheets. And you know, the every electrode has a limited current carrying capacity, which is around, say, 40 to 50 times of its diameter. Okay, so if you need a higher current for welding of thick sections, then certainly we have to go for the larger diameter. So depending upon the thickness of the sheet to be welded, thickness of the plate to be welded, the electrode of the suitable diameter is selected. Another thing is the deposition rate needed. Okay, there are two ways to increase the deposition. Deposition means how fast you are melting the electrode. Okay, so when we use the high current, say 400 ampere as compared to the 100 ampere, greater heat will be generated, so electrode will be melting fast. So if we need higher deposition, certainly we'll be going with the large dia high current. So large dia electrodes can handle the high current, so generating the higher heat, so melting rate is more, and because of the higher melting rate, your weld will be developed fast, it will be developed rapidly, and so the productivity will be high. Instead of, like, say, depositing 2 kg of the metal per hour, you may deposit 10 or 12 kg of the metal per hour also if you go with a large dia and high current electrode. Now, depending upon the DC and AC current to be used, okay, if we want very controlled heat input, like either for welding of very thin sheets or for welding of thick sheets, so here we want low heat input and here we want very high heat input, and this kind of the flexibility exists only with the DC welding because you can change the polarity accordingly. But in case of the AC, the equal amount of heat is generated in both the cases. So that's one. Then another important thing is the position of welding. If we are welding in vertical, in horizontal, or in overhead positions, then certainly we need the low heat input, because high heat input means the high fluidity, higher temperature of the molten metal, so greater tendency of the molten metal to fall down. Okay, so to reduce that, we must reduce the heat input, and that is possible only if we are using the DC. DC can work at low current, say even 50 ampere current may be good enough to have the stable arc. So low current will generate the lesser heat. At the same time, it will also be able to provide the stable arc. So welding position also affects the kind of the polarity to be used. Odd positions or welding vertical, horizontal, and overhead positions need DC. If the very thin sheets or thick sheets are to be welded, where very controlled heat is input is needed, then again DC is preferred over the AC. For higher deposition rate, if you want to use the large dia electrodes, then obviously the large size electrodes need to be used. So there are a number of situations, okay, where you may need the different types and different sizes of the electrodes. Okay, this is your welding transformer, right? So here there are two basic coils. One is primary and another is secondary. So primary coil will be supplying the domestic power supply, say 440 volt or 220 volt current. So it's a basically high voltage and low current that is supplied. And there is a secondary coil. So in this transformation process, what we get, low voltage and the high current. So low voltage, high current, this is fed to the electrode. So our one terminal of the power source will be connected to the electrode. So this is electrode holder, this is the electrode. Here arc is strike at this location. This is the base metal. Base metal or the work pieces to be joined are kept over the welding table. Okay, and this is the welding table is connected to the another terminal of the power source. Okay, this is the just to have some kind of the idea about this. I was talking about the effect of polarity and the kind of things which are formed. So this is the location, this is the typical electrode coating. Okay, this is the coating on the electrode, this is the core wire. Okay, so basically the current flows through the core wire, an arc is established between the core wire and the base metal, okay, through the weld pool. So here, and these are the inactive or shielding gas, inactive gases like CO or CO2 are formed, which will be forming the blanket or cover around the weld pool. So since the slag being so this flux acts with the impurities in the molten metal and forms the slag. Slag being lighter, so it floats over the surface of the weld, and this gets solidified eventually. Okay, and the arc of temperature typically in SMAW weld is generated of around 6,000, but in case of say laser beam, sorry, in plasma and in GTAW, it may be like 15,000, 20,000 as well. As far as the polarity effect on the weld bead geometry is concerned, this is the electrode negative polarity. Deeper penetration, large weld size because of the more heat generation in the base metal side, and this is just reverse. Less heat generation in the base metal side, about 33% of the heat generation in the base metal side, so a smaller weld bead. While in case of the AC, it's the in between of the two. Okay, this is another thing about which I will be talking little later. That's about the polarity. Okay, it's about the arc blow. But before talking about this, let me talk a little bit about the electrode designation. You see, according to the Bureau of Indian Standards, the electrode is designated using this typical sequence of the numbers. Okay, so there is a first letter. It can be E or R. Okay, so what E or R shows? E is the electrode extrusion, means the electrode has been made through the solid extrusion process. Okay, and R shows the extruded with the reinforcement, means the electrode is having some kind of the reinforcement in between. Okay, electrode extruded with the reinforcement. There is some kind of flux in the electrode. Otherwise, in this case, it is solid. Okay. The uh, second character or second character in the electrode designation, the first is a letter alphabet, the second is a number. Okay, what this number shows, this number basically shows the type of the electrode coating that is being used. So there are different types of the coatings. Mainly these are like, say, the cellulosic, rutile, basic. Okay, and then mix of their mix is also there. So the one number is for the cellulosic, the two number is for rutile, that is titania, it produces the viscous slag, and uh, three is again for titania fluid slag. This is viscous, means thick, and fluid slag means this is thin slag is produced. And these are oxide fluxes, high oxide silicate fluxes for 4, high iron oxide and silicate fluxes 5. So depending upon the composition of the coating, the different numbers are given. Okay. Then the next character in the electrode designation is a number again. So here in this 3 in category of the type of the coating shows the rutile or titania producing the fluid slag. This is the type of the electrode coating. Okay, the next character in the electrode designation is again a number which shows the welding position. Okay, so 0 is for the electrode which is good for all types of welding positions: flat, horizontal, vertical, downhand and overhead. Okay, 1 is for flat, horizontal, vertical and overhead. Okay, so the electrode, so which are suitable for the different welding positions. So 0 means it is suitable for all positions. Electrode 2 having designated say 2, it is good for flat and the horizontal position only. 3 is good for only flat position. 4 is good for flat and horizontal position in flat welding. Okay, so the third character in electrode designation is a number which shows the welding position for which the electrode is suitable. Fourth character in electrode designation again is a number which shows the type of the current or the current to be used with that. Okay, so 0 is for the DC electrode positive. 1 is electrode positive but with the current value of 90. Okay, 2 is for electrode negative with the current is 70. 3 is the electrode negative, current is 50. Likewise, so 4, 5, 6, 4 is for positive, a 70, 5, 6 and 7, these are for positive and negative both with the current value of 70, 70 and 50. So these will indicate the kind of current and the type of current and the amount of current or magnitude of current to be used. Okay, then next character is a set of 3 numbers which shows the mechanical properties of the weld metal which will be produced. Okay, or the properties of the all weld metal joint. Okay, so if what it shows, say 411, so 410, you see this is indicated by a set of 3 numbers. So 410 means if it is, say here it is 411, so what is the meaning of 410? 410 means the strength is in the range of 450 to 510. Yield strength minimum is 330, and there is no mention of these two. 411 is the most common. Say 410 to 510 is the strength, tensile strength. Yield strength is 330. Minimum tensile, minimum elongation is 20, and minimum impact toughness at 47 degrees centigrade is 27. So these numbers 4 series indicates the strength up to 400 to 510, and a 500 series shows the strength in 510 to 610, and accordingly the yield strength, like say here it is 360. Okay, here it is 18, and different impact toughness values for the minimum impact toughness of 47 at different temperatures. So minimum impact toughness of 47 for 411, it is at 27 degrees centigrade. Minimum impact toughness of 47 is given at 0 by 422. Here it gives the at minus 20. So if minimum impact toughness of 47 is given at lower temperatures, then this is good, because our weld joints can frequently come across the low temperature conditions. Okay, so basically it is the set of 3-digit number which shows the mechanical properties. Okay, and the lastly there is again last character is the alphabet, which can be in form of like H, J, K, L, P. So what is the meaning of this? H, if the last character is H alphabet, then it shows that electrode is hydrogen controlled. J means it has the iron powder, leading to the deposition efficiency of 110 to 130. K is further higher deposition efficiency of 130 to 150, and electrode L having the further higher iron powders, giving the deposition efficiency greater than the 150. Okay, and P shows that electrode has the capability to offer the deeper penetration. Okay, what is important here is like all these things must be written, all these characters must be written in a sequence, and the particular number indicates a particular thing only. If there is, say, number R, 2, 3, 4, 5, 1, 2, and H, then what it will be showing? R means the electrode is extruded with reinforcement. 2 means the electrode is of the high titanium. 3 means the electrode is good for the flat welding position. 4 means it can be used with the DC positive polarity with the current of the 70 ampere. 512 means it will offer you the strength in the range of 510 to 610, and 360 is the minimum yield strength. Elongation is 18%, and at 0 degree centigrade it will offer the 47 joule of the impact toughness. H means the electrode is of the hydrogen control type. So these must be written in a particular sequence, and each number and character has a specific meaning. Okay, so that's all about the electrode designation. Now coming to the electrode arc blow. Say this is the base metal, this is the electrode. Okay, so this is the arc. So arc is, say this is the electrode, then arc will be like this, and this is the axis of arc. All right, so arc is expected to move in the along the axis of the electrode. Okay, so if this is happening, means there is no problem, but sometimes arc tends to move ahead of the axis, or arc tends to move backward side like this. So arc can say, actually arc should go like this, but instead of going straight, arc can move this way, or arc can move back side. So instead of following the axis of the electrode, arc is getting deflected in the direction of the welding. Say this is the direction of welding, so arc is deflected in the direction of welding, or arc is deflected in backward of the direction of welding. Okay, so if with respect to this axis of the electrode, if arc is deflecting ahead of the welding direction, in the direction of welding, or if arc is deflecting in the back side. Okay, so accordingly we have the forward arc blow. So basically the deflection of arc from its axis is the arc blow, If the arc is getting deflected towards the direction of welding, this is the forward arc flow. If the arc is getting deflected in the back side with respect to the backward, with respect to the welding direction, it is called backward arc flow. Okay, so forward arc flow and backward arc flow, both are actually not good for the welding purpose. Why? Say you want to apply the molten metal at a particular place. Say this is the line along which you want to deposit. Okay, but you want to apply the molten metal here, but since arc is getting deflected, so you are not able to place the molten metal where you want to. So the first and most difficult thing, the problem which is raised by this arc flow is the difficulty in placement of the molten metal. You are not able to place where it is required. Okay, that's one. And heat is being applied at elsewhere, either forward or backward side. So your penetration, the depth up to which you are able to melt, penetration is reduced or it becomes inconsistent. You are not able to realize the depth up to which the melting should occur, and that is why somewhere deeper penetration, somewhere lesser penetration, so inconsistent welding. Third, due to the poor control over the molten metal, you are applying the molten metal at the place where it should not be. So there is a lot of spatter, or you can say the wastage. A spatter is nothing. When you have one arc, so you will see a molten metal drops are falling here and there. These are getting placed. So this is just like the wastage of the metal coming from the electrode. So that is also not good actually. Increased spatter and the wastage, inconsistency in penetration, poor difficulty in placement of the molten metal. So your welding speed is reduced because you are not able to first melt properly up to the desired depth, and then you are not able to place the molten metal at the place where it is required. Okay, so these are all these things will adversely be affecting the welding speed and the consistency. Why it is happening, that is also important to see. Okay, so let's say this is in vertical position, arc is like this. Okay, in vertical orientation, this is the power source, say DC power source. So this is the positive, say negative terminal connected to the electrode, and positive terminal is connected to, this is negative, and this is positive connected to the base metal. So current is flowing from the electrode to the arc, and then circle which will be completed like this. Okay, so here in this situation, when the current is flowing, there will be electromagnetic field will be generated around the arc as well. Wherever the current is flowing, the electromagnetic field will be generated like this. All right, current will always be following the path of least resistance. So here you see, in this situation, the interaction between the electromagnetic field around the electromagnetic field of the arc and electromagnetic field of the base, because current is flowing through the base to complete the circuit. Okay, so if this is the terminal, the current will be flowing in this way, right? So EMF, electromagnetic field of the base. It is possible that these two fields may interact with each other. So what we'll say, like interaction between the two electromagnetic fields. Whenever it happens, you will see that it is getting either repelled or it is getting attracted. So whenever there is an interaction between the electromagnetic field of the arc and electromagnetic field of the base metal, when these two interact, there will always be either repulsion or attraction. So these can go either, so this can move the arc either in the welding direction or away from the welding direction. And how it is affected, let me show you. Let's say electrode is normally held at a particular angle. Okay, this is the base, and say this is the power source, right? So when your terminal, negative to positive terminal, is connected here, the welding current after flowing through will be following this path. So the field will be generated like this, and there will be field like this. So in this case, the possibility for interaction between the two is very less. On the other hand, if you have just reverse situation, okay, just reverse situation, just assume it like this: the base metal arc, the power source, positive terminal, negative terminal, okay, and this is the arc. So here in this case, current will be flowing like this, electromagnetic field will be generated. So here there is a possibility of the interaction between the two. So if the two interacts, in this case the electrode will try to get deflect away from. So depending upon the connection of the power source with the base metal, it will significantly determine whether there will be arc blow or there will not be any arc blow, because the electromagnetic field, the direction in which electromagnetic field in the base metal is being generated, that will significantly depend upon the connection of the power source with the base metal, where it is being done. It is here, 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 or here. This is called ground connection. So ground connection determines how much arc blow will be taking place and how it can be minimized. So this is about the cause of the arc blow in the SMAW. This is mainly observed in case of the DC welding. Why? Because the flow of current is always same, the direction remains same, magnitude remains same. That is why the fields keep on interacting. But in case of DC, sorry, in case of AC, the direction means, earlier if this is the negative, then it will be after half cycle it will become positive. Similarly, if this was a negative, then it become positive. So if this is happening, the polarity will keep on changing. That the direction in which the magnetic fields, the way by which magnetic fields are interacting, that will also be changing. So the arc blow will, in one half cycle it will be in this direction, in another half cycle it will in backward direction. So actually it will be neutralized. So in case of the AC, there is no arc blow, despite of having all these kind of the interactions in electromagnetic field, because the deflection happening in every half cycle is neutralized because of the continuous change in the polarity in case of the AC welding. Okay. So what are the methods to negate or neutralize the effect of arc blow? You see, since the arc blow depends upon the electromagnetic force, which directly depends on the magnitude of the current. If possible, try to reduce the current. That's one. If possible, then switch over from DC to AC. That's the another. Third is reduce the arc length. You know, if the electrode and the base metal gap is more, there will be greater tendency for deflection of arc to the greater extent. And if the arc gap is less, the extent of the deflection that will be reduced. So reduce the arc length. Okay. There is one more practical method that is very commonly used, is especially when we are welding at the corners like this. Say, so when we are welding at the, so this is what it is shown in the top view. When this is the arc location. So magnetic field is around the arc like this. Okay. Since the magnetic field lines cannot move through the air, so these will start getting localized near the edges of the plates. Okay. And these will be more evenly distributed in the other side. So when it happens, you will notice that arc So because of this localization near the edges of the plates and localization of the electromagnetic field lines near the edges of the plates, the arc tends to get deflect like this. So arc is moving like this, but it is deflecting back. This is a backward arc flow. Okay. Otherwise, there is no arc flow in this particular case. And in forward arc flow, it will be moving in forward direction. Okay. So in order to deal with this kind of the problem, what basically we like to do is this. Sorry. Here, what we do, say this is the plate which is being welded. This is the arc location. Arc is trying to get deflect like this because of heavy localization of the magnetic lines here. So what we can do is just place a block of the metal in contact with the base metal. So the magnetic lines will also start to flow through this magnetic material. Okay, so this kind of the localization is avoided if we just place another piece of the metal in contact with the workpiece to be joined. Okay, so whenever it is done, so this kind of the localization here, this segregation will be reduced and these will start flowing like this through the metallic material which is placed next to the base metal. Okay, so this is how we can reduce. So putting a metallic block next to the workpiece also helps in reducing the arc flow. Okay. So that's all about the arc welding. Regarding the arc, the welding defect, I will be talking in the next lecture.